Subscribe now and press the bell icon. Never miss an update.
This is framing plan of steel mezzanine platform for storage purpose. So we have live load of 100 psf or 4.8 kN per meter square. I am designing steel girders to support mezzanine floor in ETABS version 19. Dimension of platform is 16.5 meter by 6.5 meter. There is 3 RCC columns of 600 mm by 600 mm in upper edge of platform in X direction with spacing equals to 8.25 meter and 3 RCC column at both edge of platform in Y direction with spacing equals to 3.25 meter, and there is 1 ms hanging column in bottom edge of platform in Y direction as I marked with circle. This column load will shift to upper floor RCC beam. This is due to we cannot place column from foundation because of entrance of building as building is in working progress. I have to just add mezzanine floor to not disturb any working. All RCC work has constructed since 2 years back. Plain beams are 300 mm by 600 mm. Mezzanine floor RCC beams are 300 mm by 750 mm in Y direction platform edge. 1 mm corrugated sheet is resting on wide flange sections and then covered with 100 mm or 4 inch thick RCC slab for finished surface. So superimposed dead load equals to 50 psf or 2.4 kN per meter square. I am providing 13 girders in Y direction with a spacing of 1.1785 meter, which will rest on horizontal girders. Also providing bracing to this girder from center to resist torsional buckling effect. Height from foundation to plinth is 2 meter and from plinth to mezzanine floor is 3.5 meter. Use FC prime equals to 4 KSI for columns and beams and grade A36 steel for MS wide flange sections. I am using AISC LRFT code for designing. Go to File, click on New Model. Choose Built-in Settings with. Select SI Unit in Display Units. Select AISC 14 in Steel Section Database. Select AISC LRFT 93 in Steel Design Code. Select ACI 318-14 in Concrete Design Code. Defining grid system with number of grids in X and Y direction is 3 with 8.25 meter and 3.25 meter spacing of grids respectively. In story dimension we have number of stories is 2. Top story height, which is distance from plinth to mezzanine, is 3.5 meter and bottom story height, which is distance from foundation to plinth, is 2 meter. Go to Define and click on Material Properties. 4000 psi concrete already defined. Click on Add New Material. Select Material Type to Steel. Select Standard ASTM A36 with grade 36. Fy equals to 248.21 megapascal, which is equals to 36 KSI. Go to Define, Section Properties and click on Frame Properties. Delete Auto Defined Properties. Click on Add New Property and click on Rectangular Concrete. Defining column of 600 mm by 600 mm with material of 4000 psi. Again click on Add New Property and click on Rectangular Concrete. Now defining plinth beam of 300 mm by 600 mm with material of 4000 psi. Click on Add Copy of Property. Now defining floor beam of 300 mm by 750 mm with material of 4000 psi. Click on Import New Properties. Click on Steel Wide Flange section. Using AISC 14 section database, select wide flange section from 8 inch to 16 inch depth with weight limit under 50 pound per feet. All selected wide flange sections have added. Click on Add New Property. Click on Auto Select List. Select all wide flange sections defined and move to right part of Auto Select List. This will useful when you are designing steel frame sections. SAP 2000 auto take steel sections from this list to assign on frame and design frame according to load on that. If auto selected frame of SAP 2000 overstress in design procedure, SAP 2000 automatically increase frame size from auto select list and redesign frame again. You will understand properly this when we are in designing phase of this mezzanine floor. Go to Define and click on Load Patterns. Add load of SDL, which is superimposed dead load in load type. Click on Add New Load. Click on OK. Go to Define and click on Load Combinations. Click on Add Default Design Combos. Check Steel Frame Design. Check Convert to User Combinations so that we can edit auto-added load combinations. UDSTL D1 is 1.0 dead load. UDSTL D2 is 1.0 dead load plus 1.0 live load, which is service load combination. UDSTL S1 is 1.4 dead load. UDSTL S2 is 1.2 dead load plus 1.6 live load. Similarly, define auto-generated load combos for concrete frame design. Go to Draw beams, columns, brace objects, and click on Quick Draw Columns. Modeling column of 600 mm by 600 mm as required. Select all columns. Go to Edit and click on Replicate. Go to Draw beams, columns, brace objects, and click on Draw beam, column, brace. Modeling plain beams of 300 mm by 600 mm as required from column to column. Go to Select, Properties, click on Frame Sections. Select plain beam 300 mm by 600 mm and click on Select to select these. Go to Edit and click on Replicate. Select Story 2 from Story tab to copy these on first story. Select all beams in Story 2, that is mezzanine floor beams. Go to Assign, Frame and click on Section Property. Select B 300 mm by 750 mm. Click on OK to change beam property from 300 mm by 600 mm to 300 mm by 750 mm. Go to Base Story. Select all column base joints, go to Assign, Joints and click on Grease Joints. Choose Fixed Joint to assign column base joint to be fixed. Go to Story 2, which is mezzanine floor. Select horizontal beams. Go to Assign, Frame and click on Section Properties. Select W section to assign, which is auto select wide flange steel section. Go to Draw beams, columns, brace objects and click on Draw beam column brace. Choose W section in property and model steel frame members accordingly. Select this joint, its hanging column joint as I mentioned at starting. Go to Assign, Joints and click on Grease Joints. Choose Fixed Joint to assign. Select horizontal steel frame members. Go to Edit Frames and click on Divide Frames. Choose option Divide into 7 frames so that 13 number of girders can be modeled. Similarly, dividing selected member in 7 frames. Go to Draw beam, columns, brace objects and click on Draw beam column brace. Modeling now 13 vertical girders with 1.1785 meter spacing. Select horizontal divided frame members from column to column. Go to Edit Frames and click on Join Frames. Go to Draw beams, columns, brace objects and click on Draw beam column brace. Modeling horizontal bracing from mid to mid of vertical girders of 6.5 meter to overcome its torsional buckling. By doing that, moment capacity of section increase than moment capacity of full span with no bracing. Select all steel frame members. Go to Assign, Frame and click on Releases Partial Fixity. Check Select Moment 2-2 and Moment 3-3 at start and end to assign release at joints. Model is showing now moment releases points in beam plane, applying UDL on vertical girders. Let's first calculate live load and superimpose dead load uniformly distributed load on vertical girders. Since we have live load of 4.8 kN per meter square and spacing between girders is 1.1785 meter and this is one-way load distribution, so interior vertical members have load come from both faces, or you can say load of one spacing, that is 4.8 kN per meter square into 1.1785 meter equals to 5.6 kN per meter. Similarly, we have SDL of 2.4 kN per meter, so interior vertical members have load of 2.4 into 1.1785 equals to 2.8 kN per meter. Edge members will have half of loads, so live load on edge vertical member is 5.6 divided with 2 equals to 2.8 kN per meter. Similarly, SDL on edge vertical member is 2.8 divided with 2 equals to 1.4 kN per meter. Select interior vertical girder, go to Assign, Frame Loads and click on Distributed. Select load pattern to live, input UDL of 5.6 kN per meter. Select exterior vertical member, go to Assign, Frame Loads and click on Distributed. Input live load UDL of 2.8 kN per meter. Again select interior vertical girders, go to Assign, Frame Loads and click on Distributed. Select load pattern to SDL. Input UDL of 2.8 kN per meter. Select exterior vertical members, go to Assign, Frame Loads and click on Distributed. Input super dead UDL of 1.4 kN per meter. Go to Analyze and click on Run Analysis. Go to Display, Force Stress Diagram and click on Frame Pair Spandrel Link Forces. Choose combination of UDSTL-D2 which is service load combination of 1.0 dead load plus 1.0 live load. Choose moment 3-3 component. Check option Show values at controlling station. Uncheck Fill diagram. Click on OK. This is moment 3-3 diagram and showing all moment values on frame members of service load combination. Right click on member to open complete detail of shear, moment and deflection of member. I will just check out deflection of members on service load combination. SAP 2000 initially take this section to be W12 by 30. I have allowable limit of deflection is L by 240, that is 8.25 meter by 1000 divided with 240 equals to 34.3 mm. Using W12 by 30 section, I am getting maximum deflection of 66.4 mm, which is more than allowable. I will not change this section because SAP 2000 will take deflection limit in consideration during design process and choose section accordingly as I selected auto list of W section. Right click on vertical girder to open its complete detail diagram. I have allowable deflection limit of L by 240, that is 6.5 meter multiply 1000 divided with 240 equals to 27 mm. Using W12 by 30 section, I am getting maximum deflection of 10.8 mm, which is less than allowable limit. Similarly, check column supporting horizontal girder. Maximum deflection of 57.4 mm, it's also more than allowable limit. Go to Display, Force Stress Diagram and click on Frame Pair Spandrel Link Forces. Choose combination of UDSTL-S2 which is combination of 1.2 dead load plus 1.6 live load. These are ultimate moment values on which SAP 2000 will design these horizontal and vertical girders. Right click on horizontal girder, maximum moment value of 284.5 kN meter. Go to Design, Steel Frame Design and click on Start Design Check. Message comes that analysis and design sections differ for 31 steel frame. This message comes because of auto select list of W sections. SAP 2000 automatically changes steel frame members which is overstressing in first attempt of design. Click on No. You can see design sections have changed as W12 by 30 was initially analyzing section. Unlock model. Go to Analyze and click on Run Analysis. Go to Design, Steel Frame Design and click on Start Design Check. Still I am getting two steel members differ for analysis and design. Click on No. Unlock model. Again go to Analyze and click on Run Analysis. Go to Design, Steel Frame Design and click on Start Design Check. This time no message come after completion of design. It means analysis and design sections have matched. Right click on horizontal girder. Design section is W16 by 50. This 0.852 is PMM interaction ratio and should be less than 1.0 to pass design check. In PMM interaction ratio, there is summation of load P, major moment M and minor moment M. Select deflection. See here 0.688 is demand capacity ratio of member in deflection check. This value also should be less than 1.0. Similarly, you can check any member interaction ratio. Design has completed here, but see, I have W16 by 50 as horizontal steel girder. Let's see if I can minimize its depth to 14 inch, as this is entrance of building, less depth will be better. Unlock model. Now change all steel sections as I was getting in design result. I am changing all 4 horizontal steel member from W16 by 50 and W16 by 45 to W14 by 53. Go to Analyze and click on Run Analysis. Go to Design, Steel Frame Design and click on Start Design Check. Go to Design, Steel Frame Design and click on Display Design Info. Select PM ratio colors and values in design output. All values of PM ratio is less than 1.0 and steel members have passed design. Right click on horizontal girder, which is W14 by 53 now has 0.895 PM ratio. Select deflection. See here 0.832 demand capacity ratio, so OK in displacement also. Click on Details to see complete section analysis and design detail. Let's check deflection values from analysis diagram. Go to Display, Force Stress Diagram and click on Frame Pier Spandrel Link Forces. Choose combination of UD-STL-D2, which is service load combination of 1.0 dead load plus 1.0 live load. Right click on horizontal steel member. Now deflection reduces to 29.4 mm. We have allowable deflection limit of 34.3 mm. Calculating demand capacity ratio, that is 29.4 divided with 34.3 equals to 0.857. Approximately same value as I am getting in design table of deflection. I will design hanging steel column which is supporting front two girder of entrance by using reaction forces coming from SAP 2000 model. If you need any assistance in structural engineering, design of steel frame structures, or you need this file, you can contact me through email address. Do like, share and comment below in comment section. Also subscribe and press bell icon so you will never miss any new video.